Hello and welcome to this tutorial about composite analysis. We will look at the tutorial from Altair with the skateboard. And as you know, or may know, composites are defined as a combination of different layers where the fiber direction of each layer may differ. And how we implement that in Hypermesh, first we want to get clear about some terms. So I made a little drawing, and in a composite optimization like in the skateboard, we will start off with a 2D mesh, shells in this case. And in the shell definition, I can define a stacking order of different plies. Plies are the composite layers with the fiber direction defined in it, and the laminate is the definition of several plies stacked upon them. So we're talking about the stacking sequence. So for the definition of composite analysis, we have to check some things which are pretty important. And the first thing is the element orientation or the element normals. So first, the element normals. Element normals meaning that every elemental coordinate system has a normal, and if two differ, the stacking sequence is always defined as from the bottom to the top. So for that reason, if some element normals are pointing into different directions, the definition would be off in terms of stiffness, in terms of element aggregation and stuff like that. So for that reason, we have to assure that every element which is in one ply has the same normal, the same normal direction. The same goes with the orientation. So maybe if I have orientation of 0 degree like that, then have an element that points perpendicular to it, or maybe also pointing in the opposite direction, then it would be not so good, because the 0 degree direction is the one which specifies the degrees of the other plies relative to this 0 degree angle. So for that reason, we have to specify every element in one ply have to have the same 0 degree direction. And just a quick reminder here with the boundary conditions and loads, we specify boundary conditions as how we want to fix the node in the different degrees of freedom. So for example, 1 to 3 meaning the translational degrees of freedom, and 4, 5, 6 meaning the rotational degrees of freedom in X, Y, Z direction. And the loads, in this case, we want to use pressure meaning force divided by area, and with that we are all set to start with the tutorial. So to begin that, we have to open a file named skateboard.hm, which you can download. I will put a link into the description, and we just take a look at it, shaded geometry. It's a skateboard with some geometry definition, and for the mesh we will make use of the symmetry. So I will switch between the PDF and here, so you can read something about composites, and here's some info about the optimization process, which is not part of this video, but I will put the other videos also up on YouTube. And now we want to mesh the geometry. So first of all, we will start meshing 1/2, then we will reflect the elements, duplicate it first, reflect it to the other side, and make the nodes equivalent on the edge in the middle. For that, we will start with a auto mesh, 2D auto mesh, or F12. I use F12 all the time. Select the bottom. That's too much. Select the bottom half of the mesh. Mesh it with 5 millimeters. Mixed elements to surface comp is correct. First order. Okay. And we have a mesh. We could define some more specific terms here, but we will just stay with the defaults this time. And the second step is to reflect those elements to the other side. For that, we go to Tools, Reflect, select all elements, specify a direction, in this case the y-axis, and the base point, for example that one. We want to have the elements duplicated, so we just press the elements again and say duplicate, and say original comp, and say reflect. Sorry, I got confused. I just read reject, but reflect. Okay, now go return, and now we have the elements on each side. Maybe just some if that was too fast, how the definition of the reflection process is made. You have the skateboard, and you have your plane where you want to reflect, and the normal vector is the y-axis, and we have to specify the base point to specify where the plane is. Okay, good. Like next step is the equivalence. Equivalence is about here, tools, edges. Now we can select all comps and say preview equivalence, and we can see here those nodes from the different elements don't know something from each other. So we have to say those are the same nodes, and this means that it is structurally coupled if those are the same nodes, and that's what the reflection process makes. And we enable the equivalence by pressing here, equivalence, and it was too fast, but left on the bottom left you could see that those elements were equivalence. Maybe make that again, say reject, say preview equivalence, and say equivalence, and you can see here 204 nodes were equivalenced. Alright, meshing is done. Now to the normals and orientation. For that we go to 2D composites, and we can first select element normals, and we just look at the element normals by selecting all and say display. In this case it is blue is the one side and red is the other side. It looks like, I will just hide the geometry. It looks like everything is set, but maybe I will introduce some inconsistencies. Just select a few elements and say reverse. Yeah, like that. Now, in this case, if it looks like something like that, so you have see that some red elements, you could adjust them like I did right with the manual selection, but there's also a neat auto option where you can just select all elements and say adjust, and there you have it. Same like before, everything is perfect. It's perfect with the normals, but not so much with the material orientation. We can see that right now. Select the comps for the material orientation and press review. Now you can see the different directions, and you see that there's a lot of opposite 0 degree directions. It's not so good, and we can just project them by make a definition here saying material orientation method by vector, and say in this case x-axis, and we have to specify a base point and say project. Comps have not been selected, I have to select the comps again, say project, and everything is good. So after the orientation and the normals are fine, we can continue with the definition of the material. We will model the material as an orthotropic material, which means that you have two values for two different directions. You specify the stiffness terms for the fiber direction and perpendicular to it. To make a material definition like that, you go into the Model Explorer and press Create Material, and you just name that, for example, CF Composite 1, for example, and change the card image to Mat 8. Yeah, I want to proceed. Let me just go that way. And now we can put in the terms. And I think I know some of them already. So the first is 110,000. The second one is 8,500. Well, let's check again to be sure. 0.3 for the portion ratio. Then we have 4,000 for the other module. So 0.3, 4,000. The density is 1.7 to the power of minus 9. 1.7 e minus 9. We have the tensile stresses. 500. The compression stress 900. The yields 58 and 170 and 80 for the shear stresses. All right. Okay, now we want to generate the plies. Ply generation is easy. You just go in the Model Explorer and say create ply. And there are several things you have to define. So first of all, the laminate definition. I will just not draw it, but point to here. So we have ply 1 with 0 degree, then 45 degree, 90 degree, minus 45, 0 degree. That's all laminate. And if you think you could use the 0 degree here and here, you're wrong. You have to define each ply independently. Doesn't matter if it has the same thickness and the same orientation. Each ply has to be modeled independently. So we generate the plies starting by 1 with a 0 degree and 2 millimeter thickness. So where's my window? Create ply. Ply 1, it's a ply. Material type composite 1. Thickness is 2 millimeters. System is generally the default system. Orientation 0 degree. Elements, we specify all elements. Proceed. And press create. Then the next is... maybe we can make it like that. Okay, second one is orientation 45 degrees. And I hope the elements are still selected. I'm not sure, but let's see if the... No, that didn't work. Because let me just check. Because the set is not specified, yeah. So you have to define the elements each time. So again, create ply. Thickness 2 millimeters, orientation 45 degrees, and elements displayed. Proceed. Okay, the next one is 90 degree. Elements displayed. Create. The next one is minus 45. Elements displayed. Proceed. Create. And the last one is, maybe that works. Yeah, same as ply 1. So it's 0 degree with all displayed elements. And that's about it. For the next thing, we want to specify a laminate. Hope so. Yeah, we will just create a laminate. Create laminate. And in this case, we can just select the plies we just created. So ply 1, 2, 3, 4, 5. 5. Oh, and I see the material definition is missing here. We'll take care of that Laminate specification is smear, and create that, and now just specify the material here to be composite 1, and now we can look if we have defined it correctly. How do we do that? We just give each ply a different color by pressing on the color and say auto color. And the second thing is we choose here property, and now we activate the composite layers. And it's not working. Why it's not working? Because one thing we have to do first is to create a p card, a property, which we assign then to the components. So we press create property, and it is a p for ply based. And we will make the Hoffman Fury and 100 interlaminar shear stress, I think, yeah, 100 and Hoffman. And now assign this property to all components. And here you have it. You see the different, maybe like that, see the different layers. And you can also look at the fiber directions. And you can see it as the first layer, the second 45, then 90 degree, the minus 45, and the 0. So everything is defined. And I would recommend that you do that before going any further, that you are sure that your laminate is correctly defined. All right. Next, we want to look at the boundary conditions and the loads, but for that reason I will just switch back to the normal view. Now we will use, first we will create some RBEs, create a component for that, naming that RBE2, and RBEs couple degrees of freedom and are defined with 1D rigids, and you may have to choose here select node, because we have one master node and several slave nodes. In this case we have, that's a pity, make that like that. Okay, great. And the second one is this one. Okay, I know it's that, so like this. And we have both RBEs. And for the load steps, we want to define the boundary conditions first. So the boundary condition is defined by analyzes boundary condition, no, constraints. And we want to hold in place the two master nodes, and in this case, because those degrees of freedom are coupled, all nodes here, we want to hold them in place with all directions of freedom, but the degree of freedom 5, because we want the board to be allowed to bend in the degree of freedom 5, which is the y-axis in this case. And create that, and you can see here that the load collector automatically got generated. We name that SPC, and now we have to create two other load collectors. The first for the load step 1 and the load step 2, which we will see what those load steps are in a bit. So we press right on the load collector and say create, and maybe load step 1 and load step 2. Now make the load step 1 current by pressing right and say make current. And now I have to look the force definition. Run on wheels. So if you have both feet here and here placed, so this will be the run on wheels. We have to define pressure. Pressure is defined with nodes and elements. We can just simply select all elements here and here. And the nodes also. That was a bit too much. Okay. And the pressure is 1.82 power of -2. And the direction is the Z direction, in this case the -Z direction. Let's just check it again, 1.82. P-load 4, create. And the second one, we switch the load collector to the second load collector by making it current. And for that we will define, I have to switch on the geometry again to be able to see it. And it is all elements between those lines here, right? No, it's much less. From this side it's much easier. So it's like those elements here, one layer too much, one too less. Oh god. Okay, now we have and we have to do it again with the nodes. Okay, that fits. And here it is -3.07 to the power of -2, I guess. Yeah, set axis again, create, and it seems right. All pointing in the right direction. Okay, we did that already. So the load steps are defined as analyzes load steps, and we have linear static load steps. Just give it a name. Let's say 1 and 2. Let's say 1 SPC and load step 1 load collector for the load create. And the second load step we will create with the same SPC and the load step 2 load collector. Create, and we're set for the analysis. We want to look at composite strains and stresses, and if we want this, then we have to define some global output requests, which we can define in the control cards. The control cards are defined in analysis control cards, and there's this button global output request. There we can enable the C stress and C strains, say as type all, and we are sure to get those stresses with the global output request enabled. I think that's about it. So we can run the analysis. Just run it in there. Should not take very long, and we will look at the displacement. Hopefully it's the same here, showing that we did not make any mistake. Okay, 0.05. Seems about right. Let's check that for us too. So we go into the contour plot and say display. Okay, 0.05. It's correct. The element stresses the von Mises 7.99. There's a 6.91 here. Don't know if that's. It's not. I don't think it's the filter. Maybe the definition has changed, or the solver did something other, but I don't know that yet. But it's in the right direction and in the right area. It's differs not so much. In load case 2, can just make a check if it's if it's okay. So we have nothing going on here and here, but bending going on at the sides. It's okay, makes sense. And for the load step 2, should have a bending in the middle. Yeah, we have. Maybe we can also show that if we make here to increase the deformation factor, maybe even more. Okay, now I can see it. How it's deformed when you put one foot in the middle. Yeah. Alright, so that's about the analysis. Thanks for watching. If you have any questions or any comments on that, I would be happy to answer them if I can. Just put them on below that video, and I hope to see you back when I put the optimization videos onto YouTube. Thanks for watching again.